Hi, welcome everyone. Thank you so much for joining us. My name is Aviva O'Neill. I'm Program Manager for Great Basin National Park Foundation. We are the nonprofit partner of Great Basin National Park, and our purpose is to connect people to the wonder of Great Basin so that it is protected for future generations. And to do this, we do a lot with education and outreach. We're doing projects with youth and schools, teacher training and curriculum. We also do a lot around the Dark Sky Initiative at Great Basin National Park. We fund interns that do astronomy programs, and we manage and operate the Great Basin Observatory, which is the only research grade observatory located in the national park. And we fund wayside exhibits and a whole bunch more. So please do get to know us a little bit more and visit us at greatbasinfoundation.org. So this is the second of our virtual lectures, which are celebrating the Lehman Cave National Monument Centennial. And I'm so excited tonight to have Dr. Louise Hose join us. We will be having 3 more of these Zoom lectures to connect you more deeply to the caves and Great Basin National Park in general. So please do check out and sign up for those other lectures. So without further ado, I want to introduce to you our speaker for tonight. Dr. Louise Hose has explored and studied caves throughout the world for over 50 years. She was featured twice in National Geographic, and her proudest achievement is placing the term snotite in a highly recognized refereed journal. She has a PhD in geology from Louisiana State University, and after completing a master's in geology at Cal State, she spent most of her early career as a professor at the University of Colorado in Colorado Springs and Chapman University. And later she served as a senior scientist for the National Park Service. And now she's mostly retired, but she holds an adjunct professorship with UNR, University of Nevada, Reno, and occasionally teaches there. She also continues her cave investigations on a volunteer basis around Nevada with a particular focus on Lehman Caves in Great Basin National Park. Last May, she led a virtual field trip to the caves of Eastern Nevada for the Geological Society of America. So we're so excited to have her tonight be talking about all the depth and knowledge she has on Lehman Caves, which she has studied a lot. And the other thing that's really neat to note is that she's the subject matter expert that often does the training for the park rangers that do the cave tours. So we get to hear it straight from the source. So without further ado, I'm going to turn us over to Dr. Louise Hose. Thank you so much.
Thank you, Aviva. I want to thank the Great Basin National Park Foundation for this opportunity to talk to you tonight. They do some great work, and I hope you will support them. I also want to mention that this is the International Year of Caves and Karst, which was extended into the summer of 2022 due to the pandemic. Lehman Caves is a spectacular world-class feature, and it's highly appropriate that it receives some special attention this year as we celebrate caves and karsts throughout the world, and more specifically, the 100-year anniversary of Lehman Caves' establishment as a national monument. Last month, Gretchen Baker shared the history and a lot of information about Lehman Caves, and I hope you caught her presentation. If not, you can view it at the website shown above, or the URL is also in the comments section. I believe it will also be included in a follow-up email following this presentation. I expect most folks in the audience tonight have taken a tour of Lehman Caves and been wowed by the spectacular mineral decorations. These latecomer deposits that fill the cave after the void developed are called speleothems, and they are composed of calcium carbonate, which is the mineral calcite. I expect most people in the audience tonight have taken a tour of Lehman Caves and were wowed by the spectacular mineral decorations. These latecomer deposits that fill the cave after a void developed are called speleothems, and they are composed of calcium carbonate or the mineral calcite. Most iconic, of course, are the parachutes in the Grand Palace. These are cave shields, and shields are the rounded plate-like features that we see. And off of the shields are draperies, stalactites, columns, and other dripstones hanging from them. The floor, wall, and ceiling of the lake room, the sunken garden, and elsewhere and along the tour are coated by secondary cave-filling deposits, and these make it impossible to see what the underlying bedrock is like, or the shape and nature of the void before the speleothems formed. We know from the work of Matt Lashnet of University of Nevada, Las Vegas, that these speleothems were mostly deposited during the Pleistocene ice ages. One stalagmite was dated at 2.2 million years old. The cave that the stalactite grew in must be older than the stalagmite itself. Thus, Lehman Caves, we know, must be older than 2.2 million years. Some calcite decorations continue to grow today, even though the majority of the calcite was put down in the Pleistocene. Then as we do tours, there are other oddities. There are these speleothems that are called turnip deposits, and they're abundant in Lehman and yet uncommon in other caves worldwide, and their development is not understood. But I have been more interested in some of the features that aren't found in other caves and are rarely pointed out on the park tours. For example, several places along the tour routes, the walls and ceilings are pockmarked or fluted. While many caves have similar features that geologists call scallops, Lehman's wall depressions are not shaped or sized like scallops that form in a cave with a river flowing through. These features are different in subtle ways, and we call them pseudoscallops. This photo, looking straight up at the ceiling, shows several interesting features. Like these ceiling channels, these are smooth half tubes in the ceilings and walls and are sometimes referred to as bubble tracks and interpreted as paths where outgassing carbon dioxide bubbles concentrated and formed an acidic stream along the ceiling when the cave was completely filled with water. The CO2 made the water more acidic and ate away at the ceiling along the track. We also see associated cupolas or domes in the ceiling throughout the cave. Unlike domes in many caves, these have smooth walls and often do not lead to open fissures or passages. They certainly are not the result of rocks falling from the ceiling because we can see their smooth walls. Given their association with the half-tube bubble tracks, the cupolas tell us that they also formed from rising acidic fluids. Then there are these half tubes or bubble tracks in the walls of the cave. Some clearly come out of small vent holes in the floor, and some lead to small domes and upper tubes. If you look at this half tube, which is in Rocky Road, it would be very difficult to explain it if it were a cave that formed from a flowing stream. A flowing stream would be going perpendicular to the path that this half tube has formed, going straight up the wall. We also see more subtle half tubes along the walls. This particular half tube is horizontal and it crosses the layering. So it didn't happen because it was softer rock or it was rock that dissolved more easily. For some reason, this formed perpendicular to what you might expect if there had been the cave had been full of water and formed in the classic ways. This is another feature that is not seen in most caves. So if you go back to your, maybe you had an introductory geology class, you probably saw a diagram something like this. Until the late 1980s, common wisdom told us that most caves formed by carbon dioxide, by rain or snow melt, picking up carbon dioxide in the air and making carbonic acid. And then that carbonic acid would sink into the ground. And once it was in the ground, it would dissolve out a passage. Commonly, that passage would be at the top of the saturated zone or the top of the aquifer. And in the area above the top of the aquifer, the water would sink in, and if it was not acidic, it might be so heavily concentrated in minerals that it would grow stalactites, stalagmites, columns, and such. And this is exactly how some of the caves in the park have formed. Particularly, an example would be the Baker Creek system, if you're familiar with it. It's still forming today, very much along this sort of model. Now, in my mind, it's a little unfortunate that Elizabeth Miller will follow me next month because she is much more familiar with the general geology of the area. And I just want to give a plug for her talk. It'll be June 1st next month. I hope you sign up for it. It's, I think, at the same link as you signed up for tonight's show. But since we didn't have her giving us the overview of geology for the area, I'm going to make a very quick introduction to the local geology as it is specifically applies to Lehman Caves. Now, I urge you, if you're not very familiar with geology, to hang in there. This will just go on for a few minutes, and I'll try to get through the geology speak quickly. And I bet if you hang in there, you'll be able to get the pertinent points out of it. Our story starts in the late Proterozoic, early Cambrian, which is about 550 million years ago, when the Prospect Mountain quartzite formed. Prospect Mountain, this quartzite was a very quartz-rich sandstone with some silt that formed in a shallow sea offshore from the North American continent. And today, the quartzite, the Prospect Mountain quartzite is best known because it forms the massive Wheeler Peak. And yet it is one of the oldest rocks in the area. So at the time that it was deposited, California and Nevada just weren't here. The shoreline for the North American continent was in western Utah, and the Prospect Mountain was being deposited right along the shore out in the ocean at that time, just offshore from the Proto-North American Craton. As time went on, the ocean rose and the shoreline went even further to the east. And at that time, further from the east, the type of sands and sediments were finer grained, and it formed the Pioche Shale. Pioche Shale was deposited in a somewhat deeper ocean offshore from the Proto-North American Craton or continent. But our most important unit to us is the Pole Canyon limestone, which was deposited in the Middle Cambrian. So these are the three units we're talking about, but this is the one that we really are interested in most. At that time, the shoreline had moved even further to the east into Utah. The area where Lehman Caves is was pretty far from the land, and a limestone formed, and it was about 2,000 feet thick at that time. Had lots of fossils in it. Following that, there was about 300 million years of deposition of other units, lots of limestone, some shales, some sandstone, some dolomites, up until the end of the Pennsylvanian. And that's a pretty long time, about 300 million years, this deposition was going on. And about 6,000 feet of rock was laid over the Pole Canyon limestone. And as a result, from that burial, from that pressure and whatever heat that generated, there was a little bit of metamorphism of the rocks, the Pole Canyon limestone and the Prospect Mountain quartzite. It was slight, and these were still, we still recognize these rocks as being sedimentary, but there was some metamorphism that took place at that time. The next thing that's important to the cave, somewhat, a little bit, is that there were granitic intrusions that occurred. They started in the Jurassic in the Great Basin and continued on, but in our area, what was really important was right in the Tertiary, right about this time, between 200 million years ago and 30 million years ago. The closest granite, so these are granites, there was also volcanism, volcanoes that erupted, but the closest granite to the cave is shown in the beige here. So the cave's over here, and the beige rock is a granite, similar to what's in the Sierra. And it is the youngest intrusion in the area, and it's been dated at 29 million years ago. The heat of this intrusion caused a second low-grade alteration of the Pole Canyon limestone that we mostly recognize by the growth of small garnets in the limestone. Then, about 17 million years ago, kind of soon after the intrusion of the granite, but really quite a while later, 17 million years ago, there was a massive event. There was a huge low-angle fault. It was a normal fault because the top slid down, and it moved about 6,000 to 7,000 feet of thickness of the sediments on top of the Pole Canyon limestone were moved away from the location from what is now the Snake Range. And they slid off to the east, and now they're founded as a contorted mess over in the Confusion Range. So that was a huge amount of rock that was removed. The Pole Canyon limestone in this area was right at the bottom where that shearing was going on. And as a result, it experienced tremendous dynamic stress and heat, and it converted itself. It was a major metamorphic event, and it converted itself into a marble. And geologists would call this kind of marble, which happens from shearing, as opposed to a lot of heat and pressure of burial, this kind of marble is called a mylonite, a mylonitic marble. And that is the rock that the cave is formed in today. For a long time, people thought that the layering that they see in Lehman Cave was what a geologist would call bedding planes. And bedding planes tell us the orientation of the original horizontal layers, and that they've been tilted. You can tell how they've been tilted, but that is not the case in here at Lehman. Instead, this mylonite, what it is telling us, informing us about the stresses that were experienced by the limestone when there was this massive sliding event that's called a decollement. So as a result, the cave is not in really limestone, it is in a marble. So that was 17 million years ago. And then about that time, in fact, that may have been part of the basin and range. And if you know anything about basin and range geology, you may know that Salt Lake City and Lake Tahoe are now about twice as far apart as they were 20 million years ago, because the area has just been stretched out, pulled apart. And in our area out there by Lehman Caves, most of this stretching occurred about 10 to 8 million years ago. It started earlier in other parts. It started to pull apart, but out in our area, it was about 8 to 10 million years ago when this happened. As a result, the basin and range is has had a lot of volcanism. It has hot and warm springs, as you may know, if you know the basin and range, or the Great Basin, you know that it has a lot of hot springs and warm springs, has a very high geothermal gradient. That's why Nevada has a lot of geothermal power plants. And it was also at this time that the Snake Range rose up above the adjacent valleys. So prior to about 10 million years ago, you would not have recognized a mountain range in this area. But about 10 million years ago, that's when the Snake Range rose up relative to the valleys around it. And this is important to our story. So if you're not familiar with basin and range tectonics, what basically has happened is the west and the east have pulled apart. The crust has thinned. The mantle and hot stuff down low has risen up closer to the surface. And because it's closer, you get volcanoes, you get heat, you get hot springs and warm springs. And when it stretched in a ductile sort of plastic way down low, but it had block faults like this, these normal faults up high along the edge of the mountain ranges. And then down low, there are these basal detachments, which are low angle faults in which the blocks slide along. Ever wonder why Sacramento Pass is the way it is, and the southern Snake Range and the northern Snake Range are kind of offset? That's because there's a little tear fault between this kind of faulting on along the way, and they're offset. When that happened, the groundwater also dropped, and that's really important. So when the Snake Range rose up 8 to 10 million years ago, the groundwater dropped. It wasn't as high in the layers of rock. The last part of our story, which you may very well be familiar with, is that in the late Pliocene and Pleistocene, way up here on our geologic timetable, there was a lot of rain and snow in the western US. Alpine glaciers formed in the Snake Range. Large lakes like Lake Bonneville formed in the basins. And our current landscape was pretty much formed during the Pleistocene. So let's look more closely at Lehman, the geology at Lehman itself, because it's not exactly like people thought it was a few years ago. Lehman Cave is entirely within the Pole Canyon limestone. Well, more accurately, within the Pole Canyon marble. But if you go up on the surface, the old geology maps, any geology map you find, except for some notes, some rough ones that we've done recently, will tell you that all of this is marble, or actually limestone. But if you go up on and walk over the surface and map it, it turns out that a very large area is quartzite. And the quartzite covers much of the cave. So the red markings you see, it's basically the outline of the cave. And if you went on a tour, you would come in here and you would go up to about here, and then you would come back and come out over here. But most of the cave that you don't go into these days is underneath the quartzite on the surface. There also happens to be some shale, but that's not that much important to us right now. Why is the quartzite there? My best guess is that it is a fragment. It was just a piece that got ripped off during the Decollement event and plopped right there and left behind. Now, the old timers in the audience may remember when tours went through the talus room, the largest room in the cave. It's about the size of a football field, and you can't really see from one end to the other due to the piles of talus. Most likely, the rocks and boulders on the floor fell when the water table dropped millions of years ago. The ceiling height in some places is about 50 feet high. And as you look around, you see very few speleothems, very different than the rest of the cave. This is because it is under the quartzite on the surface. And as a result, water on the surface has been diverted away from this area. It doesn't sink in and come down into the cave. It gets diverted away on the surface. And speleothems don't have a chance to grow except where there are fractures. But things get even more interesting when we go into the gypsum annex, which is a little entrance right here, a little crawlway right here, goes into the gypsum annex. And it's a wonderful area to inform us about the cave. It's a different world in there. There are few calcite speleothems as the overlying quartzite has protected the area except the long fractures. Most of the walls are covered with mineral crust of gypsum and calcite, and often those crusts have detached from the wall, have pulled away from the wall. As a result, most of the floor in the passage is covered with the detached pieces of gypsum, which is a different mineral, it's a calcium sulfate, and calcite crust. There also is a distinctive keyhole cross-section to much of the passage. Because of the lack of infiltrating water from the surface, there are a few mineral deposits or speleothems. So the gypsum annex is really important because it gives us a glimpse into what the entire cave likely looked like before the Ice Age. So here we're looking straight down at the floor, and there is a hole in the floor that goes into a passage much too small to go into. This hole at one time allowed warm water to rise up through it and into the cave. So instead of water coming down from the surface, water was coming up through holes like this one and into the cave. And then later, when the water table dropped down, warm, moist air came out and formed this rim of minerals that have deposited around it. This is called a rimmed vent. And that they formed when they hit the cooler cave air. If you look straight up in the cave, you see a lot of domes and cupolas in the ceiling of the gypsum annex. Scattered throughout the gypsum annex are small yellow crystals dispersed within the gypsum crust. Chemical analysis by my colleagues at New Mexico Tech show that the mineral contains uranium and vanadium, and it is probably a rare mineral called metatiaminite. Metatiaminite is commonly associated with sulfur-rich environments at the time of crystallization. Metatiaminite is present in Carlsbad Cavern and its neighbors, the spectacular Lechuguilla and Spider Caves. All three of these New Mexican caves are well established as having formed in a sulfide-rich environment. Thus, metatiaminite's presence in Lehman is suggestive that the passage is also formed in a sulfide-rich environment. But the most intriguing site to me in Gypsum Annex is this spot. Here we see some of the same features we noted in the other more decorated parts of the cave. We have a horizontal half tube that trends kind of parallel with the cave, and we have the general keyhole shape to the passage. We also see pseudoscollops on the overhanging wall and deep dissolution rills or grooves that are on the vertical part of the wall. These are the characteristics of what we call acid pools that form in caves where warm, sulfur-rich water rose from deep in the earth to the floor level. Most of the passage would have been just above the water table level at the time that these features formed. So to explain, I'm going to take a quick trip with you to southern Mexico to visit a cave that is currently rapidly developing thanks mostly to rising sulfide-rich waters. And this cave, I think, is very much like probably the most active phase of development for Lehman. So the cave is Cueva Villa Luz. It is a 1.5 mile long cave in southern Mexico. The stream that flows out of it is white because of all the suspended sulfur and bacteria in it. Let's look at the cave profile first. Notice that there are an abundance of little streams or springs coming into the cave. So there are inlets of water coming into the cave in many places throughout the cave, and there's far more than are shown here that we've identified. And one of the features is that there are often domes very close or a little bit downstream from where the springs come in. And these domes or cupolas formed because the spring water is heavily charged with hydrogen sulfide, that rotten egg-smelling gas. When hydrogen sulfide gets into the air and mixes with water in the cave, or oxygen in the cave atmosphere, it forms sulfuric acid. And that sulfuric acid eats away at the rock above the springs. Now, this cave has a very toxic atmosphere. It can have very high sulfuric acid rich atmosphere. Hydrogen sulfide in the atmosphere when we've been there has commonly exceeded 210 parts per million in some parts of the cave. Carbon dioxide has sometimes dropped or sometimes risen to more than 3%. Oxygen has dropped below 16% several times during our visits. We don't know the exact numbers because all of these exceed the limits of our portable gas monitors. So as a result, of course, we wear filters all the time, and we carry air tanks for when the carbon dioxide gets too high or the oxygen drops too low. So when the water comes out of these springs and hits the air-filled passage, the hydrogen sulfide is released from the anoxic groundwater, the groundwater that has no oxygen, free oxygen in it, into the air. And the air does have oxygen in it. So two important reactions can occur. The first is that the hydrogen sulfide and the oxygen combine and deposit sulfur. And we see the elemental sulfur in some parts of the cave. The second thing that can happen is that the hydrogen sulfide and the oxygen combine and form sulfuric acid. Now, both of these reactions release energy, and that has allowed bacteria to take the energy and use it in place of sunlight. And so they don't need sunlight. They live off of this chemical energy. And the cave has a very robust community of bacteria that facilitate and make a living off of these two reactions. The most charismatic of these bacteria communities we call snottites. They have the physical characteristic of phlegm. If you blow on them, they wave around and they stretch just like phlegm. But they drip highly acidic sulfuric acid with an average pH of 1 to 3. And we've even measured negative pHs dripping off of the snottites. Lots of organisms live in them. They are not a single type of bacteria. They are communities of bacteria and fungi, and they even have invertebrates that live inside the snottites. So the warm water, as it rises from the spring and condenses on the cave on the cave wall, it forms sulfuric acid, And the cave wall is calcite, calcium carbonate or limestone. The sulfuric acid will attack the limestone, and there's a conversion that happens. And the limestone changes itself into gypsum, a different mineral, calcium sulfate hydrate. The gypsum manifests in two ways. In some places, the gypsum is selenite, this crystalline needle type of gypsum. And in other places, it's what we call gypsum paste, which is a microcrystalline form of gypsum. And the gypsum paste flows. It has very low structural integrity. It flows and it even drops off spontaneously. Hapless cave explorers have it fall on them. This can be a problem because there's lots of moisture in both of these types of gypsum, and the moisture has a pH of about typically 2 to 3, so very acidic. One of the more interesting, to me, probably the most interesting part of Cueva Villa Luz is the Yellow Roses passage. In Yellow Roses, there is a spring rising up into a room, very high in hydrogen sulfide, no oxygen, free oxygen in the water. It sometimes also releases carbon monoxide and formaldehyde. Notice in this cartoon, you have a narrow fissure where water's coming up, a notch in the walls right at the top where the water, right above where the water hits, overhanging wall that is coated with sulfur and selenite, and a dome. And this general feature is really very similar to the acid pool that we saw in Lehman. Elsewhere in Cueva Villa Luz, here's another acid pool. It has a spring that rises up over here, and it may well have other springs underneath the muck, little ones coming up underneath the muck, but there's a fairly big one right here. Steep bedrock walls that form a channel, a shelf that puts a notch into the walls, overhanging wall, a dome ceiling. And this is, again, a classic acid pool. The gypsum paste that is on the wall is full of moisture. The gypsum paste sometimes falls off of the walls and the ceiling. If it falls into the stream, it will dissolve immediately, and that's part of why the stream is so white. If it falls onto the shelf, it will gather there as white sediments until a hurricane comes along and the water rises up temporarily for a while and removes all that material. And if you're wondering what all these dots are, they are little tiny fish, they're mollies, and they live off of the bacteria that is either falling into the cave like snot tites or coming out of the spring, the little filaments of bacteria. Incredible ecosystem in this cave. So this is, this particular acid pool looks more like this. Again, you've got steep bedrock walls with water coming up. You've got the shelf, the notch in the wall, and the dome, very similar to the shape that we see in the gypsum annex, throughout the gypsum annex. Underneath the gypsum paste on the side walls, there is acid, sulfuric acid that is formed. It goes down the walls and on the overhangs, you get indentations in the wall, very much like the pseudoscallops. And this is apparently how pseudoscallops form, is from this moisture where the wall is overhanging. Where the wall is not overhanging, you get, and particularly on this shelf, you get these very deep grooves that are dissolved into the bedrock from the sulfuric acid that has run down the wall or dripped off of the wall onto the shelf. Again, in Villa Luz, we see the same sort of shape. The channel is a steep bedrock channel. There's a notched area that is just above where the main flow is. And then there is a dome-shaped ceiling, or in some cases, even an outlet, an entrance above. So let's take this back to Lehman Caves and how it informs us about Lehman Caves. From what we have seen at Lehman and at Villa Luz and other caves like Villa Luz, it looks like we can best understand Lehman's history as a three-phase development that shaped the cave. First, there was rising acidic waters, water that was in an aquifer that probably contained both hydrogen sulfide and carbon dioxide, as does the water in Villa Luz. And it filled whatever the fracture was. And along the ceiling, you would get these grooves and the domes forming. Why along the ceiling? Because the carbon dioxide would come up. When it got near the top of the water table, it would get released and become bubbles and concentrate up high and make that water more acidic than the water down lower. The other thing is hydrogen sulfide. Hydrogen sulfide is very soluble, so it doesn't tend to form bubbles, but as soon as it hits the top of the water table, it gathers up oxygen that is seeped in from the surface, forms sulfuric acid, and then it is gangbusters in dissolving out the cave. So the first stage, we would have had these warm acidic waters coming up. This was because the area has lifted up the way it has, this almost certainly happened on the order of 10 to 8 million years ago, a long time ago. As the Snake Range rose and the regional, and as a result of the Snake Range rising and the water table dropping relative to the rocks during this 8 to 10 million years ago, we got to the point that it probably was much like Villa Luz. Water was coming in through those vents and getting the oxygen in the air, forming hydrogen or sulfuric acid moisture on the walls. The walls were probably coated with gypsum paste. That's probably when the metatiaminite was deposited. There may have been sulfur on the walls. There was probably lots of microbial activity at the time, and the cave would enlarge very quickly as it did in Villa Luz. And this was likely to have been in the 10 to 8 million, probably more like 8 million years ago. After 8 million years ago, when the range had really lifted up, the water table dropped, the acid waters no longer came into the area, acid gases didn't come into the area, and the cave for a while was probably just kind of abandoned. But during the Pleistocene, with all the snow and rain that came in, that water infiltrated down to the cave, made its way down, dissolved a little bit of calcite as it made its way down, and then when it hit the cave and the pressure dropped, it deposited these stalactites, stalagmites, shields, and various speleothems. And that water would have dissolved any gypsum that was in the cave, where it got to, and would have dissolved any sulfur. So it removed our best evidence of how the cave formed in the southern part of the cave, and it got covered up everything. But we are so fortunate that the Prospect Mountain quartzite block was left on the surface over the northern part of the cave. And as a result, not very much water infiltrated into the cave during the Pleistocene. It didn't reach the passages like the gypsum annex. And to a large extent, we still have the gypsum annex looking very much like it probably did when the cave first dried out and was abandoned. We do not have much biological activity going on today. That has gone away, but we have the gypsum, we have the metataminite, we have in some places vents in the floor to give us a pretty good idea of how it all formed. There is a fourth phase, the story of what's going on today, and that's a story of condensation corrosion. It relates to the atmospheric conditions in the cave and how those atmospheric conditions are corroding the walls and speleothems. This is naturally happening. This is not vandalism, but that's a story for another day. I thank you for your interest in Lehman Caves and our work. If you wish to delve into this topic in further depth, you can download our Geological Society of America field guide chapter on the hypogenic karst, hypogenic being a fancy word for something that formed from water rising up from down deep. Karst of the Great Basin at the URL on the screen, and I think it's in the chat, and it will be in the follow-up letter. Before I end tonight, I want to thank the many photographers who have graciously shared their work with me. And my research colleagues, particularly the New Mexico Tech folks and the park, Gretchen Baker of the Park Service, Doug Powell from the Forest Service, and a good friend and fellow geologist, Harvey Duchesne. And now I'd be very happy to answer any questions that I can.
Well, thank you so very much. That I have to say for myself, I am not a geologist, and this is all completely new to me, and you described it so well that I feel like I understand the cave, which is amazing. So let's look at some of our questions here. One question is, what is causing the stretching of the basin and range?
Well, I'd like to defer that, and you should talk to Elizabeth Miller, who's studying some more general geology next month. But it's a complicated answer, and I don't believe anybody has a definitive answer. But it has to do with the large-scale plate tectonics and the subduction that's happened in the San Andreas Fault and things like that. But that'd be a great question for Elizabeth Miller.
Yes, and she is our speaker next month on the first Wednesday, same time. So, you know, that's her specialty, 40 years. She's a Stanford professor, 40 years in geology. So we're having some amazing subject experts here. So my next question, will climate change have an impact on the cave environment? Or as a cave, is it relatively stable? And will it not be affected by climate change?
Well, of course, in the long term, it will be affected. Everything pretty much will be. Caves do dampen out things. They don't respond as quickly, and they don't respond to sort of the wild changes. And so Matt Lashnet, I encourage you to look at his work. He has been looking at the speleothems in Lehman Cave and elsewhere, tying it into climate change. Caves are wonderful laboratories for studying climate change because they don't respond to annual kinds of changes. They really respond to the longer term, broader changes that occur. And obviously the cave in 8 million years has gone through a lot of changes. And as I said, right now, carbon dioxide in the cave is creating a lot of corrosion of the cave. And it's not artificial, it's just the natural evolution. So there's no doubt climate change will impact the cave, but it will probably be subtler and slower than the impacts on the surface.
Thank you. Okay, next question. Outside of the Snake Range, are there other examples of this type of cave formation in North America?
Oh my gosh, yes. Yeah. It's one of those things that once we came to recognize it, and for the most part, that was in the mid to late 80s when we came to recognize this form of speleogenesis, you see it everywhere. And one of the problems is there are a lot of caves that probably have formed this way, but like Lehman, because later on they get infiltrated by water from the surface, sometimes I think there are a lot of caves that started this way and we don't realize it because water from the surface infiltrated, found this tube that was great to use to pass the water through and obliterated the evidence. But for example, pretty much almost all the caves down in the Guadalupe Mountains where Carlsbad Caverns National Park is, almost all those caves form through this sort of mechanism. As a wild guess, I haven't done the statistics on it, but I would guess that at least half the caves in Nevada were formed through this sort of mechanism, and probably at least in Western Utah, probably as well. Arizona, Grand Canyon, South Rim of the Grand Canyon, most of the caves on the South Rim of the Grand Canyon form this way. There are caves in Virginia that form this way. So it's actually fairly common, but it's a relatively new way of looking at caves. And so it's growing, our list is growing.
So yeah, it's really interesting. And you were basically the one on the team of the ones that discovered this whole thing, right? So that's pretty neat.
Well, I got in on it early, but no, I wouldn't say that we discovered it. We have contributed a lot, but if there was a discoverer, it may have been Stephen Eggemeyer back in the 70s up in Wyoming, who also applied it to Carlsbad Caverns, and his work really only got recognized after he'd passed away, unfortunately.
So yeah, we still have a bunch of questions here. So the next one is, what is the source of the hydrogen sulfide that rose from below that generated these features? And then the person wrote, I know that in, I'm going to say this wrong, Lechugia and Carlsbad, we have a lot of hydrogen sulfide from fossil fuel bearing strata in those basins.
Right. Right. The isotope work that's been done so far by Zoe Havlina at New Mexico Tech suggests that it's probably more of a magmatic sulfur. So sulfur can come from, hydrogen sulfide can come from various sources. As the person said, the Carlsbad Caverns, Guadalupe Mountains seems to be mostly derived from petroleum. A cave over in Italy that's very well known for Sazi, it seems to come from evaporites that have been, this gets into too much chemistry, but evaporites that have been reduced into hydrogen sulfide. In our case, Zoe's working on it. She's only got a little bit of data, but so far it's pointing towards a magmatic source, whether that is the granites or, I mean, I think one of the things that's exciting, I have been doing all of this just as a volunteer, retired old geologist that wants to have some fun. But I think one of the exciting things is that this could be associated with the same sort of processes that put in some of the valuable mineral deposits, the fluids coming off of magmas that put in fluid deposit or mineral deposits. But the answer is we don't know.
Still lots to learn. So I will throw in here that there's a few fun comments. One, a comment on how lovely your nails are and supporting
The Ukrainian nails.
another comment on your earring and wondering if that was an ammonite. Looks like
It is. It is.
Okay, now we'll go back more to the serious ones. So a person was asking what kind of fossils are typical of the Pole Canyon Formation, if you happen to know that.
For Elizabeth Miller. Since the one part and creature, I'm sure we can look at that together. I know who wrote that. Yeah, it's since the rock I'm looking at has been so metamorphosed, none of the fossils have remained, and I've never worked in that area on the rock. Otherwise, I don't know.
Yes, so that's for next month. But this might be for next month too. There was a question on how, when the ground became marbleized, kind of like how long it took to happen, but that might be for Elizabeth.
No, I don't think Elizabeth has looked at the Mylonite marble.
Okay.
I talked to her one time or exchanged notes with her, and I don't think she was aware of it. It's a very small area, and that's why it got missed by people like her on the mapping. That it's just a small area that the cave happens to be in. And how long would that take? I don't know. I don't know how long it took for the Decollement. It probably took as long as that sliding event took to happen. And I'm afraid that's something that Elizabeth might be able to answer. What she probably won't be able to answer that rock, but she probably could answer how long it took for that block to slide across.
Right. There's a question. Someone would like to know if you happen to know about the Yahi tribe caves in the Ishi wilderness of Northern California, if you happen to know how old those are. Have you ever heard of those caves? No. Okay.
No, and no, and that might be the lava bed caves, in which case they're not very old, if they're the ones in Lava Beds National Monument, but I'm not sure.
Okay, I'm not sure either. So a question on, let's see, I'm trying to see which one of these we're almost at 8 o'clock, which there was a question on asking if you could re-describe them. I can't even pronounce this right. The Decollement, that's when it was like falling off, right?
Yeah, I can. I suspect that Elizabeth will talk about it a lot next month, but I can do a little bit. Let's
also, maybe that one could be when we send out the recording. You know, I know a lot of this information was super dense. So if you're interested in getting a little bit, you know, kind of back into those specifics, we'll send out an email with the recording and some links, the links that were in the slides. I think
that's a good idea, but let me say real quickly, basically what happened was about 6,000 feet of overburden, a rock that was over the area, was a big landslide, a gigantic landslide, something bigger than we've ever dealt with in our historical time. This big landslide went off over to the east, and it's a massive, massive slide. And what I don't know is, and it's something I guess I need, I'll see if Elizabeth tells us next month. I'm excited to hear her talk. I don't know if that happened over a month or it happened over 500,000 years. I don't know. But it was basically a huge landslide of about 6,000 feet of rock, thickness of rock, and massive, many, many kilometers of rock that slid off to the east. And it's world famous, very, very famous.
Well, let's have this as our last question. and you may not have much of an answer, but you'll have, I think, something to give us, which is a question on the cave turnips. Someone's just curious about how they formed. I know is it still just a complete mystery, or is there a little information there?
I would say it's a complete mystery.
Ah.
Yeah. I talked once with Carol Hill, who some would say is one of the 2 leading experts in the world on cave minerals. And she made a suggestion that they were related to welts. And not that anybody knows what those are, but I've been looking at them and I can't see that what she said made sense. And that's not to criticize Carol at all, because she's never studied these particular things. It was just a guess that an educated guess. And I don't know, because they are concentrically banded. That last slide I showed, that showed layers that had been corroded away and looked like an onion that it's kind of exploded a little bit. That's what they're like. And I have no clue of how they form. I know that there was a young person who was going to be studying them, and I know also that Gretchen's not on, but I don't know if he's come. He was from Worcester College, and I don't know if he's come up with anything or not.
Well, as there is with all of science, right? We're always learning new things. That's one of the, fantastic things about living here together on planet Earth. We have so much to learn and explore, and I think we've all, I'm sure, gained a lot of information and understanding tonight. So thank you so very much. We did have a bunch of chats and people writing in how much they appreciated this program tonight and your knowledge and your enthusiasm. So thanks everyone for coming, and we hope to see you next month.